Hi students, welcome back. Lesson 18, Video A. We've dimmed the lights so you can hopefully pick up the data on the slides there in the videos. We're changing gears. We're in the very last part of the course. The previous three lessons we worked with categorical variables, p-hat stuff. We did hypothesis tests for population proportions. We did confidence intervals for population proportions. And in the very last lesson, we looked at comparing two populations, categorical variables. The last four lessons, I guess we're on 18, 19, 20, and 21, quantitative variables, numerical variables that calculating the average makes sense. And we're going to be working exclusively with means. In this lesson 18, we're on video part A. We need to do the theoretical models that sort of exist in the background that allow us to develop formulas for confidence intervals and the methods for hypothesis tests. In this lesson, this is the theoretical chapter. We're going to make a lot of assumptions about the population and develop those models. Okay, so this is a little bit of a trickier chapter, but you can handle it. To the slides here, lesson 18, we're modeling the sample mean. That symbol is Y bar. We're done with P's, we're done with p-hats. Now we're moving on to sample means, it's Y bar stuff. Lessons 14 to 17 dealt with categorical variables. Right? Are you prepared for retirement or aren't you? Coming from the very last lesson. That's categorical. When we always summarize those with proportions. For this, there was one set of rules. Same techniques are coming. Confidence intervals and hypothesis tests. There's one set of rules, one set of models. Okay, and we're good at that because we've been doing it for a good 3 weeks probably. Now, to wrap up this course. Lessons 18 up to 21. Sample mean Y bar. We're looking at the other kind of variable, quantitative. And the statistic that we will use, sample means. It's a measure of the center. So we're doing quantitative variables and sample means. When it comes to like the quizzes at the very end of the course, final exam, very end of the course, the problems will be intermixed. Your first step is what kind of variable do I have? Do I have a categorical variable or quantitative? And then if it's quantitative, it's means. You have to decide that first to make sure you're using the correct techniques, the correct technologies, the correct models. We're still working towards cooking up a confidence interval, running a hypothesis test. Okay? To do that, we have to step backwards and develop that theoretical model for Y bar, the sample mean. We've done this once for proportions. If we took repeated samples from our population, in reality, when we want to run a hypothesis test, we'll take that one single sample. But we have to realize, students, that what if I took multiple samples, right? The data that we collect is not the end-all, be-all. We could have gotten different data from that random sampling. Okay? The theoretical model that we're going to work with provides all of that framework. Here's the example. We'll use it because it's pretty familiar to most people. We'll look at IQ scores of Cecil College students. Okay. The ideas are familiar, and IQ scores follow a normal model. The mean is established for IQ scores, it's 100 points, and the standard deviation is established, it's 15 points. So we have a variable with a very well-known model that describes the behavior. What I did, I made up a data set. It's probably realistic. Pretend that I knew the IQ scores of all 2,500 or so Cecil College students. You can see a little portion of that. Hopefully the video picks this up, but it's in your notes. All right? Here's the first student, IQ of 97. Here's the second, IQ of 75, 98, 95, 111, all the way right. I don't know how many data values are on this, but not 2,500. I mean, this keeps going down to the floor and down to the next floor down. That's the population I'm sampling from. Suppose I want to investigate, hey, students at Cecil College, is there any evidence that our mean IQ score is any different from the general population? right? General population has an average IQ of 100. And maybe for fun, I'd like to test if Cecil College is any different than a mean of 100, okay? We believe that Cecil College students are no different than the general population when it comes to IQ. No better or no worse. But who knows? Until we might actually collect some data to test that theory. We'll take a sample of 100 students, randomly selected from that whole population of 2,500. We'll do it this Saturday. We'll administer IQ tests. And so pretend I did that. Here's the data on the next slide. 10 in each column, 10 rows. Those are the 100 IQ scores. So first student IQ of 81, second student IQ of 69, so on, right? Some of those IQs are above average, some of those IQs are below average. I'm sure, yep, there's 100 here. Okay, that would be the first sample. And now imagine in your head. Maybe we don't need to imagine, but just from this data, calculate Y bar. That's the sample mean. Now, you don't have to do this. I mean, you can pull out your calculator and add up these 100 values and divide it by 100. Or if it was in StatCrunch in one column, just hit the summary stat button, you would get that Y bar. I have no idea what that number is. In fact, if I just peek at my notes here, I don't have it. Maybe it's 102.8, maybe it's 96.99. Who knows, okay? The idea in this chapter is this. What if I just said, throw those data values away, put them back into the general population, take another sample, and then go again, and go again. Infinite number, just keep taking samples of 100, keep giving those IQ tests. Based on this sample, I could run a hypothesis test to determine if the mean IQ score at Cecil College is any different. Right? We could. We're going to develop those ideas. But what we have to remember is that, well, to run the test, let me clean this up here. To run that test or to compute a confidence interval, I would need that theoretical model for Y bar. Right? I would need that theoretical model for the sample mean Y bar. We've already determined this for p hat. We've already done this back in lesson 14 for the sample proportion p hat. And now we're changing gears. The theoretical model is based on taking repeated samples. In practice, we don't do this. This is the theory. Clearly, IQ scores would change. If I took a second sample, and in your notes you can see that second sample. Right? These data values are different. Right? These are 100 different students, and so these are the new IQ scores, and I could calculate Y bar. Again, I don't know, maybe put a little subscript too, because it's the second sample that we theoretically could take. Is that Y bar going to be the same as the first one? Of course not. If the true mean here at Cecil for all of our students is 100 for the IQ, shouldn't that Y bar be pretty close to 100? Right? Might be a little bit higher, might be a little bit lower, but that's the idea. It's like, how does Y bar behave? I need a model for Y bar. Interesting stuff when you think about it. Couple bullets at the bottom. We must imagine taking repeated samples, always of size 100 in this example. Each time calculating the mean and then determining the correct theoretical model for Y bar. Once we know the correct model for Y bar, then in the final 3 lessons we're going to develop those methods to do a confidence interval and to run a hypothesis test. Computer simulation was performed. When we wrote the notes on StatCrunch, you could run simulations, so I did it. It wouldn't translate very well to a video, so here's what I did. Sample sizes of n equals 100 were generated. IQ scores were simulated. And each time the sample mean was calculated. If you flip the page, students, here's a dot plot. 2,000 samples I generated on StatCrunch. Each sample was 100 students, and each time I calculated that sample mean. Notice I got a ton of dots, real close to 100, right? If we believe that the true mean at Cecil College is 100 for IQ, most of the time my sample means are very, very close to 100, right? What do we got to fill in here? What theoretical model should be used for the sample mean? Well, if I showed you this picture and I said, guess the model, I think at this point in the semester, pretty much everybody would say, well, you know, it's not perfect, but if I had to guess, it sure looks pretty normal to me. And that's what goes on the line, right? If the conditions are met, we'll talk about them briefly. If the conditions are met, y bar will follow a normal model. For the theoretical model, what value would you guess for the mean? So, if I said pick a number that's the mean of this theoretical model, I sure hope that we'd all come to the same conclusion, right? I think we would say, cool, sure looks like 100 to me. You know, maybe a little bit different from 100, but theoretically, if I kept going, I mean, that's 2,000 dots. Crank that up to 20,000, 200 million, and I think that in the long run, this would zero in right here at 100, right? The standard deviation, careful here, it's underlined. The standard deviation of individual IQ scores comes from that normal model, the parent normal model, the population. What did we say a couple slides ago? Individually, IQ scores have a standard deviation of 15. Now look at this picture. This is the distribution of y bar values. Sure looks normal, sure looks like the center is 100, and what's the glaring difference? Does a standard deviation of 15 fit here? Surely it doesn't, because if I went about one standard deviation out, I should be up to what, 115. If I went one standard deviation down, I should be down to about 85, and for one person at a time, that model would be the right model. But here, clearly the standard deviation for this theoretical model for the sample mean is much smaller than 15. When I take a group or a sample and average out those values and start to look at how the sample mean varies, sample mean varies much, much less than individual values, right? This is much, much smaller. I think at the bottom, I want to squeeze in a little note here. And it says take our word, and I don't think this showed up on the slide, so let me just clean this up a little bit. There's a little note at the bottom of that page. It says, take our word, the formula for the standard deviation of the sample mean. So, it's going to sound funny, but it is correct. I need the standard deviation of y bar. Know that difference. Y are individuals. Y bar is that sample mean from 100 IQ scores. Standard deviation of y bar, the symbols would look like this, sigma of y bar. It's a subscript, it's just a label. Take the standard deviation of y bar for this model. Here's what we would do. We would take the standard deviation of y and divide that by root n. Okay? And that divide by root n should sort of remind you of the proportion problem, because square root of n showed up in all of those p-hat standard deviations. Okay? Now, if I calculate this for this particular example, what's the standard deviation of IQ scores in general? It's 15. What was our sample size that we took? It was 100, right? So 15 divided by square root of 100, well, root 100 is 10, and 15 divided by 10 is about 1.5. And see the bullet point? Clearly the standard deviation for y bar is much smaller than 15. It has to do with collecting lots of data and sort of averaging it out. I don't expect to get a mean IQ from 100 students, like at 120. That would be just so unusual, because I would have to randomly select like the 100 smartest students on campus. That ain't going to happen. So there's much, much less spread in Y-bar, and that's the huge important takeaway point from this video. And now, like, a 1.5 makes sense with these tick marks, right? If I jump out about 1 standard deviation, I'm at 101.5. If I jump out 2, I'm at about 103, and so this is going to come up again and again in this unit, and especially in this lesson and the next. So we'll conclude that one here. There's a part 2 coming up. We'll wrap up this example. So see you in a minute.